Chapter 5, Earthquakes. Experiencing an earthquake firsthand. The science of ghost forests and mega earthquakes and how we know about them. Faults, earthquakes and plate tectonics, seismic waves, and earthquake detection. Measurement of earthquakes and earthquake hazards. Experiencing an earthquake firsthand. January 17, 1994, Northridge, California. Structures like this apartment building were damaged by an earthquake. 57 people were killed and 9,000 were injured. I remember this earthquake very well. More than 2 million people are killed by earthquake hazards in the 20th century. 30 million U.S. citizens in earthquake hazard zones right now. Most deaths are due to building collapse and tsunamis. The Indian Ocean tsunami claimed more than 230,000 lives. There are ghost forests in Alaska and along the coast of Washington State. Stands of dead trees in coastal marshes in Washington State are similar to trees killed in one of the largest earthquakes ever recorded, which was in Alaska. Were the Washington trees a signal of a past mega earthquake? Well, radiocarbon data indicated that they died between the years 1680 and 1720. Was there a possible earthquake source nearby? The location of the Cascadia subduction zone relative to major cities of the Pacific Northwest. Well, here's Washington and Canada, and up here would be Alaska. So the subduction zone of the two plates, right here, where one plate goes under the other. That would be a place where earthquakes would occur. Mega earthquakes occur along subduction zones. The Cascadia subduction zone is approximately the size of the rupture zone of the 2004 Sumatra earthquake, which was the location of the Indian Ocean tsunami. A Cascadia subduction zone earthquake would have generated a substantial tsunami. Well, where's the evidence of the tsunami? Look in the soil and the layers. The tsunami sand deposits cover soil in Oregon in the top, and this is Chile right here in the bottom. This was a tsunami in 1960 that had occurred, and it deposited all this sand as it rolled on shore. Here's a tsunami in the 1700s. And there's the evidence of it right there. Tsunami-generated sand deposits were discovered in coastal marshes of the Pacific Northwest. They are similar to sand layers formed by the 1960 Chile mega earthquake and the 2004 Sumatra earthquake. On the basis of historical records, Japanese scientists hypothesized that the Cascadia earthquake occurred in January 1700. How did American scientists test this hypothesis? Well, there's a fault, a fracture in the crust on which movement has occurred. You can see it's quite a long fault right there. And you can see in the photograph up here, this is where the fault line is. And here it is in the drawing. Earthquake features. Only part of a fault may move during an earthquake. A fault is a fracture in the crust on which movement has occurred. A zone of weakness where earthquakes occur. The focus is the location where movement begins on a fault line. The epicenter is the location on the surface above the focus. It could be up to 800 meters apart, the epicenter and the focus. A fault scarp, or a step in the land surface, formed by the movement on a fault. Only part of a fault typically breaks during an earthquake. There are 3 types of faults. Faults are classified by the relative movements of rocks on either side of the fault surface. So this part could either move up or that part moves down. That's a normal fault line right there. Here's a reverse fault where the slant has an overhang. Here's a strike slip fault. A normal fault is a block above an inclined fault. It moves down. The reverse fault, the block above an inclined fault, moves upward. And a strike slip fault, the blocks on either side of the fault move horizontally, either left or right. Faults recognized by observing offsets of features or change in the elevation of land surface. Horizontal fault movements. The road was, remember in the picture, the road was damaged and displaced by a fault. There's a fence that had moved 3 meters by San Francisco earthquake in 1906. We'll go back and look at this. There's the fence. That's how much it moved. That's quite a bit, isn't it? And the vertical fault movement. Here, in 1964, the rocks at land surface offset to form a fault scarp by a big 1964 Alaskan earthquake right here. Stream offsets in California. Stream channels offset by recent movements of the fault. Right here is the same spot as right there. Fault movements are driven by stresses which are produced by plate tectonics. The stress continues to build. The rocks closer to the fault bend like an archer's bow. And then the earthquake happens. The rocks spring back and they vibrate. The friction along the fault surface is enough to cause most faults to stick. All rocks are slightly elastic. The buildup of stress causes the rock to deform or to change shape. After decades or centuries, the stress has built up to sufficient levels to overcome the friction, and it causes fault movement, thus your earthquake. The recurrence interval. Time for buildup of stress to cause fault movement and earthquake. Well, there are longer recurrence intervals, 100 years for the biggest earthquakes. It's decades or less for the smaller events. The scientists can analyze the buildup of deformation using instruments called, there's creep meters, strain meters, and they use satellites as well. The seismic gap. Segments of active faults that have not experienced recent movements. In 1999, Izmit earthquake in Turkey occurred in a seismic gap. Major fault breaks in segments. Several segments of the North Anatolian Fault broke during previous years to produce big earthquakes. A fault is a plate boundary between Anatolian plate and the Eurasian plate. And there they are right here. The Eurasian plate up here and the Anatolian plate down here. And the fault line, very close to the Black Sea. As you can see, earthquakes and the plate tectonics and the faults pretty much line up together. There are a lot between Eurasia and Africa here. It's around the Pacific Ocean. Most earthquakes occur along the plate boundaries. There are relatively few in interiors of plates. However, they do occur within the interior. Think of your fracking earthquakes. Shallow earthquakes are much more common than deep events. Divergent plate boundaries at the ocean ridges are characterized by earthquakes with shallow focal depths. The largest earthquakes found in association with convergent plate boundaries. The largest earthquakes are found in association with convergent plate boundaries. Convergent plate boundaries, the ocean trenches, are characterized by earthquakes with a range of focal depths of 0 to 800 kilometers. In the United States, the earthquake damage occurs in the most populous of California. 62% chance of a large earthquake in San Francisco Bay Area by the year 2032. It's not very long from now. The largest, most frequent United States earthquakes are along the convergent plate boundary south of Alaska. The Charleston area had a huge earthquake. If you visit there, you can look at the historical buildings. They actually installed earthquake bolts. They run the entire length of a house, and they work. Those homes have been standing there for hundreds of years. Seismic waves and earthquake detection. The movement on a fault produces a fault scarp. This little area right here, the fault scarp. There's a zone of no offset along the fault where nothing seems to have moved. Seismic waves are vibrations caused by an earthquake. They travel in all directions from the focus. They're recorded on seismograph instrument. A seismogram is printed record from a seismograph. I was on a school bus in the 1960s and experienced an earthquake. I was on the bus and we were in a flat area where telephone poles actually ran along the side of the road. The bus stopped as soon as she realized there was an earthquake going on, and as we looked out the window, I could see the telephone lines, the waves of telephone lines. One would be up, the other one would be down, and the wires were whipping up and down. So I could see the waves of the earthquake. Here are surface waves. That's what I was actually looking at as evidenced using the telephone poles and the wires going up and down. This is a station near the focus, which was right here, seismograph station A. The P waves, the highest velocity waves, and the S waves. A station far from the focus experiences a little bit less. The variations are smaller. There are two forms of seismic waves, P waves and S waves. There are slower surface waves that travel along Earth's surface, and there are faster body waves that travel through Earth's interior. The Rayleigh waves result in vertical movement of surface. These are two types of surface waves, Rayleigh and Love waves. Love waves produce a side-to-side movement. The Rayleigh waves produce a vertical movement. The surface waves are responsible for much of the earthquake damage. They were definitely responsible for those telephone poles and the wires going up and down. The seismic waves and earthquake detection. You can see these are transmission lines. These are not the types of telephone poles that I was looking at. I was looking at regular distribution lines, the wooden ones. This is a Rayleigh wave. And this would be a Love wave. The side by side motion. This is supposed to be a straight road, but because of the waves, it has given it a left to right. It has given it a left to right, an S shape. Seismic waves and earthquake detection. If you were to put a slinky and bolt it to something solid and begin to play with it, there are things called, there's the primary wave, where the wave would move from here. If you pushed it in, it would move from here to there, to there, to there. And what do you think happens after? Well, the energy doesn't just disappear. You can't make energy and you can't destroy energy. It has to go somewhere, so it bounces back and it begins to come back. The P waves are the first to arrive at a seismic station. They're 4 to 6 kilometers in the crust. They compress material parallel to the direction of travel. The slinky analogy. The slinky analogy is the P waves. So, the secondary wave here kind of shakes it up and down, and the particles move up and down, and that movement continues on down the rope. That's the wave propagation, the secondary wave. The S waves, secondary or shear, arrive at the recording station after the P waves, but before the surface waves. They are 3 to 4 kilometers in the crust. They vibrate material perpendicular to the travel direction. The wave in the rope analogy, going vertically. It cannot pass through liquids. For example, the outer core. Here are distances where the seismograms were located. Denver, St. John, and Lima. And the farther away they are, at different times that these waves arrive. The time it takes seismic waves to reach a seismic station increases with the distance from the focus. The time interval between the arrival of the P, S, and surface waves also increases with the distance, and that is shown here where these lines are farther apart. The farther away it is, the longer it takes for those waves to arrive. The difference between the arrival times can be used to estimate the distance from the earthquake. For example, Denver is closer to the epicenter in this particular graph. The data from multiple seismograph stations are needed to pinpoint the location of the earthquake's epicenter. So they compare all of these seismograph data in order to figure out where it is. And when you get several seismographic stations that have the waves arriving very close together, then they know that that's very close to the epicenter. There are two methods of measuring earthquakes: the magnitude and the intensity. The magnitude is the standard measure of the shaking and/or energy released from an earthquake, calculated using a seismogram. The bigger fault motions produce bigger earthquakes. The intensity is the measurement of the effects of an earthquake on the people and the building, or the damage. So, the magnitude is how much shaking has occurred. The intensity is measured by the effects of an earthquake on people and buildings, or how much damage has been done. A comparison of the relative amounts of ground motion and energy released from earthquakes of different magnitudes. A 1 would be very little. But look, a magnitude of 9, the ground motion, that's quite a big number, the energy released right there. It's huge. A magnitude is measured on a logarithmic scale. Each division represents a 10-fold increase in the ground motion. Each division represents a 32 times increase in energy released. For example, a magnitude 5 earthquake exhibits 100 times more shaking and releases nearly 1,000 times more energy. Now this graph shows several different earthquakes. A great earthquake in Sumatra, Indonesia, and the Krakatau eruption, magnitude of about between 8 and 9, and over here, look how much energy has been released. These are pounds of explosives. The Charleston, South Carolina earthquake right here was only about a magnitude 7 earthquake, and it released this much. Look, the Hiroshima atomic bomb released less energy. It released less energy than all of these earthquakes put together. The Northridge, California earthquake. If you were watching the World Series, you would have seen the earthquake occur in 1994. The ground started shaking and everyone in the stadium, they all left. There is no maximum value for magnitude scale. Earthquakes are described as minor to great, as magnitude ranges from 3 to more than 8. The largest measured earthquake was in Chile in 1960 with a magnitude of 9.5. There's an informal designation of mega earthquakes for events of magnitude 9 plus. The intensity is measured using a modified Mercalli scale. There's a 12-point scale using Roman numerals. The higher values depend on the ground materials and other factors. The effects of earthquakes on people and structures. Number 1 would not be felt by people. Number 5 would be felt by nearly everyone, and many people would be awakened from sleep. Dishes and windows would be broken, the doors swing open or closed, unstable objects would be overturned, and liquids would slosh around in containers. Your fish tank might lose some water, and some fish might get thrown out. Magnitude 7, it would be difficult to stand. Drivers would notice. Large bells ring. It would be slight to moderate damage in ordinary structures. Now, the earthquake I was in the school bus, was not 7, not 6, not 5. It was probably more around a 4. My fishbowl did fall down and break, and my fish was gone when I got home from school. It just slid off the counter. Magnitude, or the higher ones, the higher intensity, the higher magnitude scales. The intensity is measured using the modified Mercalli scale. Difficulties in comparing earthquakes from different regions due in contrast in population density, building codes, ground materials, and distance. Really, if the earthquake occurs in the wilderness and there's no buildings or people there, how intense is it? The intensity is measured using the modified Mercalli scale, useful for rapid collection of online data following earthquakes. The USGS generates community interest intensity maps. For example, the 6.7 magnitude for the North Ridge earthquake in 1994. Note that the damage is not distributed uniformly with distance from the epicenter. A strong magnitude 6.7 earthquake was the most recent to strike developed area. That's just in the United States, and since then there have been more intense earthquakes. Hazards associated with earthquakes include the ground shaking, aftershocks, landslides, elevation changes, and liquefaction, and tsunamis. Here's the map of the North Ridge earthquake, where different things had occurred. Like this bridge, this part of the bridge was up here, and it just fell onto the lower level. The ground shaking can be exaggerated by weaker earth materials. There's less shaking for bedrock. There's more shaking for soft mud, sand, and gravel. The landslides that are common on steep slopes when shaken. There were 11,000 landslides associated with the North Ridge earthquake, and 3 deaths were associated with inhalation of dust containing fungal spores. These tree stumps from Sumatra were originally on dry land. They were broken off by the Indian Ocean tsunami and dropped below sea level by fault movement. The elevation changes result from movement on faults. Mountains east of Los Angeles raised by 1 meter during the Northridge earthquake. Smaller islands near Sumatra were uplifted 1 to 3 meters, which exposed the coral reefs. Liquefaction occurs when water is released from saturated earth materials that are violently shaken. Material loses strength and collapses, causing subsidence. This car is partially swallowed by liquefaction during an earthquake in New Zealand. Apartment buildings collapsed to liquefaction after the 1964 earthquake in Japan. Tsunami. Fault displacement of ocean floor displaces large volumes of water. This is often associated with subduction zones. It moves very fast, up to 960 kilometers per hour. Low waves in open ocean, but can pile up tens of meters. Low waves in open ocean, but can pile up tens of meters of water along the coastline. Friction along a segment of the plate boundary locks the overriding plate and the subducting plate. For example, the Australian plate, Indian Australian here, and the Eurasian plate there, and the water above. The shape of the overriding plate is distorted as it is pulled toward the subduction zone as the lower plate continues to descend. This can continue for hundreds of years. The stress finally breaks the locked portion of the fault, which results in an earthquake. When the plate snaps up, it causes the seafloor to move upward, pushing the water out of the way and forming a tsunami. The tsunami moves outward from the source area at speeds of hundreds of kilometers per hour. How long did it take the Indian Ocean tsunami to reach India? 2 hours. It took it 7 to 11 hours to hit Africa, depending on where it was, and 20 plus hours in South America, 29 hours to North America. The tsunami damage. The waves reached an elevation of 31 meters. Tsunami heights along the coast of Japan for the Chile and the Cascadia earthquakes. Comparable wave heights interpreted to indicate mega earthquakes of similar magnitude. The variation in wave heights related to differences along the coast. Water levels were both above and below low tide level. Multiple tsunamis are associated with a single earthquake, especially the Chile 1960 earthquake. There was approximately 10 to 30 minutes between the wave crests. The sand deposits generated by the Indian Ocean tsunami are similar to those produced by the tsunami after the 1700 Cascadia earthquake. And that's evidenced by the layers in the soil. This concludes Chapter 5.